All right, let's talk about the addition of a halogen to an alkene. So we're going to talk about the mechanism and stereochemistry. And here's the reaction. As you can see, we have an alkene, which is a carbon-carbon double bond. We're adding a halogen, in this case, bromine, and we're resulting in this product. And this product is known as a vicinal dihalide. A vicinal dihalide is two adjacent carbons with halogens on them. In this case, it's bromine. So the reaction is stereoselective, and it makes the anti-addition product. All that means is we add bromine to the top face of one side of the alkene and the bottom face to the other side of the alkene. So add one to the top, add one to the bottom. And the reaction generally uses bromine or chlorine, not iodine or fluorine. And the reason for this is because iodine is slow to react and fluorine is pretty explosive. So, mechanism. This is going to be a two-step reaction. So, step one, we're going to take a pi bond from the alkene. And this is going to act as a nucleophile. Remember, there's a lot of electron density there. And it's going to attack the bromine, which is going to be our electrophile. And it's going to generate this cyclic intermediate structure called the bromonium ion. So, as you can see, we have our pi bond attacking that bromine, and those electrons are going to essentially push the two bromines sigma bond that connects them onto one of the other bromine, onto like the right side, the right bromine, which is going to make our bromide anion. And then the bromine on the left is going to connect to those two carbons and form this cyclic positively charged structure called a bromonium ion. Now, why exactly does this occur? Why do we have this cyclic structure? So we know the Br-Br bond is easily broken when the pi electrons attack the electrophile. And we know that there's no carbocation intermediate. So if we had a carbocation intermediate, it would be pretty unstable. Experiments show that it's not there. But the bromonium ion actually is able to be there and be somewhat stable enough to be an intermediate because it spreads charge density across both of those carbons. So if you were to look and draw the partial positive charges in, you can see that the positive charge from that bromine is spread on both the left and right bonds between carbon and bromine. So both those carbons are partially positive. And what this means is for our next step, we're going to see that the bromide ion attacks from the back, causing a transaddition. So if the carbon is partially positive and we have a bromide anion, then those negatively charged electrons are going to go and attack that partially positive carbon, which is going to push the bond between the carbon and the bromine up, and it's going to make this product, which is our anti-addition product. So you can see the bromine attacked the bottom, pushing those electrons back onto the other bromine, so the left bromine is sticking up and the right bromine is sticking down. You could see how if the bromide anion were to attack the left carbon, then you would have the down bromine on the left carbon and the up bromine on the right carbon. And you can also see how it can't attack from the same face, because if you, like, for example, make a molecular model, try to imagine this in your head. If you have two carbons and a bromine sticking up between them, the other bromine has no space, takes up too much space, so it can't go down from the top. So that's why it goes and attacks from the back, causing this transaddition and making the anti-addition product. All right, let's talk about the stereochemistry. So if the starting alkene is optically active, then we're going to have a racemic mixture of enantiomers that are going to be generated. So let's take this structure of cis-2-butene, and we're going to add bromine. As you can see, we get two enantiomers, but if the starting alkene is actually not optically active, a meso compound will be generated. So let's take the example of starting with trans-2-butene, and we're adding the bromine. Here we can see that the bromine, they're both going to be on the same side. So yeah, we do get these two products, but if you look, they're exactly the same thing. It's just flipped. So these are a meso compound. It's the same product. So in other words, if the starting alkene is optically active, such as a cis-2-butene, then you're going to get a racemic mixture. If the starting alkene is not optically active, such as trans-2-butene, you're going to get a meso compound. And that's it. Yeah.